will be now
Okay,
active.
thank you. Please start.
Thank you. We will continue with, we will see something about possibilities to do symbolic computation in computing today will be aimed to computation of different classes of generalized inverses. First, using GIAN neural network, ZNN, and then using back and present our main motivation in paper published in Neurocomputing. From error. This error function is aimed to computing matrix inverse. Then next step was star AV minus A star. This model is applicable and result is, in this case, result is inverse of A star, left inverse. We have dual case of this here. Dual case can be considered in analogous value. Regularization parameter and this model can be even rank deficient, such ZN mass matrix is ensured using small here results. Here result is A minus 1, there result is, here result is A dagger. And next, matrix G of T instead of matrix G of T. Solvable, not consistent. Then A star A V minus A star, if we multiply, which are always solvable, but ZNN requires invertibility to put plus lambda I, lambda identity matrix. On V of T converges to lambda I inverse when time tends to infinity of V of T, exact result. Here depends on initial states. As T tends to infinity, G of T minus 1 G of T, and it is well equal to range of G and null space. In that way, we will obtain outer inverse with prescribed range. Finite time convergence can be obtained using appropriate, we mentioned several finite time activation functions. Does not exist always, we can find better. Many people put terms to improve convergence is require in that paper we used error function e.g. defined as A of T here should be plus lambda identity matrix lambda should not too small, not too big. Small values, very small lambda, we can have computational problems. because of singularity. Matrix A is from rank R. G is of rank S, where matrix A. And we spoke that in case S equal to R, we will obtain reflexive inner inverses, 1, 2 inverses, when rank of matrix G. And then we developed a design dot of EG, dot of our error function. It is possible to use presented in this way. And we will not repeat today again. Shortened form, which uses, I should put here, G of, I forgot to put here that G1 of T, it is shortened notation, G dot of T, G1 dot of T, here will be G of T, A dot of T, minus gamma, I will skip not of T, V of T, and as usual, I changed V to X, V dot plus G1 EG, oh, we can write here as EG of T. G1 is equal to G of T, A of T plus lambda E. Is easier to trace. Looks not so complicated. Left and right. Then as I minus G1 of T. Minus time derivative of G1 of T. Here is theorem. This convergence of Z and N dynamical system. EG is forced to 0. G of T, A of T. Z and N dynamics force EG of V of T will tend to 0 as G of T, A of T plus no outer inverses. The particular choices of EG of T error function can be found. We will obtain model for computing usual matrix inverse of T equal to A star gives ZNN model. Please. G of T, here. A is given matrix M times N of rank R. G is S, which is less than or equal to rank of A, and rank of G. G is arbitrary matrix defined a calligraphic.
In previous slide.
Previous slide.
It is
Last night it requires modifications. First, X dot is V dot typically, but many journals require similarity no greater than 25%. Several publications we need to change notation for non. It is because of technical requirements. Such similarity reports are from one side good. Then if we use again g of t equals a star, so g of t is arbitrary matrix, another conjugate transpose when lambda inverse, which is Moore-Penrose inverse. But if we use conjugate transpose, arbitrary matrix, and here is possibility to compute the Draisine inverse. We spoke that using directly matrix power and then develop because of many terms required to compute this power. Here is another. This improvement generalization assumes transition from g of t, a of t, plus lambda I, v of t, g of t plus times a of t plus lambda I, v of t minus f of t, not calligraphic f, usual f, which means another n times n matrix. Is of dimensions. Yes, n times n. V dot is of, since A is of dimensions m times n, V dot must be of opposite dimensions because V of t is m. So f of t should be of dimensions n times m. Fg of t. And this expression is defined using two arbitrary matrices. Requirements for matrix GR in previous case. There are these requirements. For matrix f of t, I can say that only dimension n times m is required in the matrix f of t. We can, of the form EFG dot minus gamma EFG of t. Here is linear model. Oh, sorry, here is V of t. V of t here, sorry, remove dot here, V of t. It is error function. Can we write here G1 of t, for simplicity. We will have model dot of G1 times V of t V dot of t minus F dot of t. Accordingly, we will obtain G1 of t, V dot of t. It will go on opposite side with minus. Here is equal to minus gamma E Fg of t minus F dot of t minus gamma plus F dot of t minus gamma E Fg of t. H is the same as nonlinear activation function f. It is more general model. What will be result of this ZNN model? If we run ZNN design, evaluate Fg error function to 0 when as t tends time t. What does it mean? G of t t minus f of t will time tends to infinity only if we use appropriate nonlinear activation. We can predict finite time convergence. Tends to 0, so according to invertibility of GA plus lambda E, we will obtain V of t tends to G of t F of t. And in this way, we need to compute limiting value, limit as t tends to infinity of different expressions G of t, A of t, plus lambda I minus 1 inverse time Simulink implementation. There in this Simulink one subsystem is included. This subsystem is included because of better readability. After that, the output. Two inputs, matrix G and A, are required. We need multiplication. Here is identity matrix, parameter gamma, the same block as it is for gamma. And after that, complete Simulink is developed. Where is 1 by S? I'm trying to find first 1 by S. If you analyze Simulink model, you should find first 1 by S. No, Sylvester equation. Here is 1 by S. X of 0 is defined here. And the input in 1 by S is derivative of V or of X. Here is defined input in 1 by S. Here is one term, I minus G1. Okay, I will write one step more. V of the dot of V of t, we will put in left-hand side and in right-hand side is equal to I minus G1 of t V dot of t minus G1 dot of t V of t plus F dot of t minus gamma E F G of t. All these terms must be included here, sometimes with plus, with minus. Here is minus gamma E F G with minus G1 dot x with minus F prime, F dot with plus. F dot with plus. And after that we have defined x dot. Then x dot goes in integrator. Output is x. And after that in exit, if time interval is finished. If not, we will continue in next time instance. Here we trace Frobenius norm of error function G1 of t, x of t minus f of t. Here is table which defines possible cases in a general model. Here we will analyze many of them. G1, A, F, G. I must write once more because in right hand side of table I cannot see. V of t plus lambda I, V of t minus F of t. We have many possibilities now. Then I analyzed limit representations of generalized inverses. And moreover, limit representations of different expressions which involve generalized inverses. So we were able to find not only relations of several expressions which include generalized g of t equal defined as 0. It will give, computation will give e of t minus I. Second choice, f of t equals g of t with e g of t, and result outer inverse with range and null space of t equal to f of t equal to a obtain model for computing Moore-Penrose inverse of time varying can be defined as how L is less than or is greater than or equal to by to choose greater values than index. Index will be better. If we choose greater values than index, the result will be the same, but equal to index of A. Another here is notation for it is AL, A 2L plus 1 star AL. It is it is power of Drazen inverse. Here, f of t is defined as a power L. It is GA power K. We can put index. Because here is GA in equal to K, then we will obtain result equal to power of Drazen inverse. Another choice, this choice, GA, G is the same, nothing to do with G, and choose f of t equal to, it will not be f of t, it will be f lambda I. Then we will obtain this model. F is constant matrix lambda I. G is arbitrary. We will arbitrary according to presented conditions, opposite dimensions, requirements on rank, and so on. Result will be ideal. And so on. There is limit expression for A Drazen. k minus 1, because here is GA. F of t is here. I put in this paper also this possibility, A of t minus x dagger. Of course, the result will be A dagger. And I think we have time to see ZNN model for solving system of linear equations. This model is much simpler than considered models for computing outer inverses of even more complex and more general ZNN model for computing different expressions involving generalized inverses. Our goal now is to define ZNN for solving by a linear system. Equals B of t. Yes, after all, this problem is not difficult for us. Error function, here I used small e to define error function. Probably bold e is best choice because capital letters we will use for matrices. Small letters we will use for scalars, scalar values, and bold for vectors. Here we have, of course, vector. A is matrix. X is vector from by only n. Only n, it is vector n by 1. N by 1, and we write only n. And B is n by 1, or only we will write n. E of t is defined as A of t, V of t, minus B of t. So here, if we consider lambda x, probably that some kind of eigenvalues can be found. It will be interesting to consider in any case. P dot of t equals A dot of t, V of t, plus A of t, V dot of t, ZNN model, say of t, plus A of t, V dot of t, minus B dot of t, E of t, A of t. It is vector. It is vector here. It is more correct. Will not be visible. A of t, v of t minus b of t. Equals minus a dot of t, v of t, e of t. Or v dot of t equals identity. But what if A is not square matrix now? It will be not true identity matrix. Is it correct to put here Mn means matrix of dimensions m times n, and with ones along main diagonal, but in non-square case. Probably minus a of t, v dot of t, plus b dot of t minus gamma e of t. Calligraphic G is the same as calligraphic F. Again, similarity works. It is to change. Please here consider I as a possible non-square matrix. We will have ones, we will have 1, 1, 1 in main diagonal, but it can, and here is simple, after all, model. K is GIAN parameter. Of course, we will stop here. Questions, if you have questions.
Any question, please? F of t in previous model.
Do you know
After convergence or?
this slide?
Yes, yes. Of introducing f of t.
Varying.
So in earlier case, we
One more f of t.
Why you have introduced this, he is asking.
Here is another is minus gamma, nonlinear activation. V minus f. And here is another f, but this f and f dot arises from time derivative and only error function. Here is minus gamma, error function. Using derivative. Because in derivative, then times v of t, and then plus GA plus lambda I define E dot first.
To
Thank you.
So maybe
AX equal to lambda x. Here was B of t. Probably is applicable. Probably. lambda x, we can try. And it can be applicable in time varying case. Is it okay to consider time varying case?
We can consider time varying case also. This instead of that we can write this lambda t and this x t. Okay.
It is. We can
Okay.
analyze.
Thank you very much. Now our second lecture will start. So he will be talking on GNN for solving the matrix equation BXCA B equal to B. Okay.
Mainly this talk will be aimed to computation of generalized inverses.
Okay, please continue.
And particularly we will investigate application of GNN model in practical implementation and symbolic computation. Both GNN model and symbolic computation will be considered. Before all, I will show you one very useful representation of generalized inverses. This representation is applicable to outer inverses. Very useful representation and applicable to many classes. Expression B, CA, B1, B. Corresponding B, CA, B1, C, B and B, C and C. A is given matrix M times M of rank R. B is of dimensions, I forgot, N times P. C of dimensions, Q times M. And we consider such it is one inverse, arbitrary one inverse, inner inverse is there. In computation, best choice for one inverse is to use Moore-Penrose inverse. We will use Moore-Penrose inverse mainly. Why to use another one inverse? Here, one inverse can be arbitrary. Result will be the same. It is interesting. We can change one inverse, but if some specified conditions are satisfied, result will be the same. What is result? What are results? 1, 2, 5 are results. Result 1 says x equals to x is in class of inner inverses of A, CAB is equal to rank of A will not be visible. Equal R, for example. Several classes of outer inverses with prescribed range and or null space. Sometimes only range, sometimes only null space classes of outer inverses here. Set of outer inverses. Now null space star is in place of unknowns which satisfy Penrose equation 2. Range calligraphic is equal to calligraphic GIAN dual case star in space of range. We are not interested in to know null space equal to null space of C. It is that null space of such outer inverse is equal to null space of C. Inverses with predefined both range and null space. Because this outer inverse with predefined range and null space inverse, and according to that, between BC inverses and such inverses. Only one such set reduces to on range and null space. And how to recognize this? X belongs to set of outer inverses dot range R of B if and only if rank is equal to rank. Can I continue here? Rank of B. In one moment, such expression will compute outer inverses with precision. X belongs to set of outer inverses with precision of CAB is equal to rank. The same expression, but the result is different. X is equal to predefined range and null space is unique. B is equal to rank of B equals, and of course there is always color reflexive inner inverses. Rank of CAB are equal to inner inverse if well-known representation. Outer inverses of rank R. R is rank of A, is this. And now we can try to compute several classes of G inverses or several G inverse we can compute using this representation. Moore-Penrose, of course, why I ask to find in this paper. Moore-Penrose is first. Range equal to range of A star, image equal to N of A star. According star A star, arbitrary one inverse, A star directly compute Moore-Penrose inverse. We need to define matrix A first. Try with one symbolic example, if possible. Visible? Here is one example with parameter t. Sometimes we should say mathematically that parameter t is real. Otherwise, the result can be transpose A of A dot, and then use okay. Symbolic, efficient but limited. Simplified. Great job. Original Murpenros's inverse was very complicated. After obtain much simpler result. Here is pseudo inverse. Then we can compute the Racine inverse of A is outer inverse with range R of the same of the same matrix AK. Here will be AK, AK. Representation of the Racine inverse. In this way we can, of course, more panels. We first compute find index of matrix A for. It means that index of it will be group inverse. Is 1. Index is equal to 1. A trace in quickly. A pseudo inverse of A3. Simplify first. Probably simplify will do something on this expression. We can verify if this matrix is Racine inverse. How Racine inverse? Verify equations 1k. It is 1, 2, and 5. Equation 1. Simplify. Surely simplify. Otherwise, it will not be equal to 1k. Okay, we can write it and it will be equation 1. Simplify. I will not try without simplify this. And again, I will apply simplify on complete result. Where is my cursor? Really? 1k equation is satisfied, then verify equation 2. It means A Drazin, A dot A dot AD minus AD should be 0. I expect that here result will be complicated and we will not obtain B. Better choice. Try. If not, we will apply again, simplify. So rule is apply and apply simplification. As I expected, I wanted to put once more simplify and some simplifications. Powerful function simplify is able to do such simplifications. And we need to verify one more equation. It is group inverse.
The pseudo inverse of A, and in this case for Drazin inverse and pseudo inverse expressions.
Pseudo inverse. Outer inverse with prescribed range equal to range of A power k and null space defined by the same matrix is equal to A power 2k plus 1. Moore-Penrose, it is according to general formula presented in this way. Drazin inverse equal to group inverse, of course. Because index is equal to 1. We computed rank of A, computed rank of matrix powers will be the same. And decided index k is equal to 1. And here we used only A dot A 3 times matrix power used, and again A. All kinds of outer inverses with predefined range and or null space are of the same form. We will be able to compute arbitrary, very powerful representations. Very powerful representation. Here is one general equation 5. Minus. Probably result will not be 0, but it is 0. Only requires to simplify such expression, surely. The equations and can we use one matrix with index greater than 1? Here I have one such example. Where is this example? Constant case, it was, here is. Here is another example. I can put here A or B. Rank of 5 of A dot A 4. We must compute then we can stop. It means rank of matrix A is equal to 2. Index of matrix A. Index is equal to. And now how to compute Drazen inverse? AD in this case is equal to, we will first compute AK, it will be power, matrix power of A2. Probably better choice was A dot A, but too late. For AD small to make difference with the previous example. Equals to, yes, it is AK dot pseudo inverse AK dot A dot AK dot AK. Simplify is not necessary. And then verify equations. First one is matrix AD minus AK. Or better choice here was to, if we ask question of the following form, equal, 2 times equal. Otherwise, 1 plus plus, true. It's true, say, Mathematica says, we can verify matrix equations in that way also. 2 AD dot AD minus AD. Can we ask equal AD? True. And yes, Mathematica has three equal. It means really identical, structurally identical. Structurally and with values identical. Can we compute more appropriate and core? Can I find here for core defined range and null space? Here I have no this representation. Can find core EP. It is the it is very important. I will save this. Core EP is defined as A power K more Penrose. Simply it's equal to A power K. Cannot see now core EP. ACP A key. And that way it is easy. The formula is even simpler. Times pseudo inverse of A key times A. And in that way you can compute many different. We can try with our symbol. Here we need A, D in capital letters. I'm trying to find the representation of core EP inverse in form of outer inverse with predefined range. We'll be able to compute core EP inverse using Urquhart inverse is equal to outer inverse equal to range of A power k core EP inverse is star A k plus 1. It is because of A. No, one. More Penrose here. Dot pseudo inverse transpose, yes, in real case, transpose of A dot AK is more correct. Dot transpose not equal shapes. What was rank in this case in symbolic case? AK is still time. Simplify is there is much simpler form of many classes of G inverses. I don't believe a lot in such DMP after that. MP them are outer inverses with prescribed range general space and they future properties of G inverses, but investigate properties of such expressions and it's okay. Investigating such combination, core EP, of course, well known. DMP is if such inverses, this Urquhart formula is very how to investigate future properties. It is okay to investigate such properties. And say core K more Penrose. Of course, this expression investigated a lot, and we can see in literature to such combinations of different. Can we find something more? Core in case if index is equal to 1. So we can easily define, ZNN model can easily define GIAN. Only we will consider will not be so easily. And it requires different technique. Day after tomorrow, we will see possibility how ZNN model can solve system of matrix equations. Possible we can find CMP in this form. I will try to find in this book only one. Okay. We will consider also DMP inverse, defined as combination of Drazen and Moore-Penrose inverse. DMP, D dagger, A D dagger is equal to A Drazen, A dagger. Where is this? Here is. So we can compute DMP inverse immediately, even in symbolic form. A Drazen, A dagger. We have already computed A Drazen. Only to capital A Drazen for symbolic form. We need this. Then DMP, A DMP of A pseudo inverse of A. Simplify. It is the DMP inverse of A. And here we investigated some representations of DMP inverse. Outer inverse. A DMP dot A DMP equal A. Simplify first. Equal to ADMP. Simplify in fixed form. Renal space. And we compute this inverse using several representations. can verify some of properties of DMP inverse. Here are some of properties. Which one we want to verify? First one, for example. AK A dagger A. It is AK. It is only AK. A star. Okay, first write AK D and P equals to AK A star. Best choice is to divide windows. AK, we have AK dot ADM DMP equals to AK dot pseudo inverse of A. Okay. I wanted question equal. I spoke several times. Don't forget another equal. Because of that, I wanted B for another example. We will use this symbolic matrix. Rank of A. So here will be only Drazen inverse. I want to confirm again. AK is equal to A, index is 1. Simplify. Simplify in any case in right hand side. It's true. Without simplify we will not obtain formally. Okay. Time is over, Safik. It's time for questions.
Okay, thank you very much, Professor Predrag, for your wonderful talk. Now,
method to compute generalized inverses. So how this method, the ZNN and GNN is better than?
It is possible to use ZNN and GNN because we have approach for outer inverses with range and null space. And here we developed a GNN model in computing DMP inverse. Here is, and we will analyze in third lecture after lunch. We will analyze this model. This model is based on matrix equation 7, 6. Because G can be considered as A power K, and here is A power K multiples of A, G, A, X equals G. And we developed GNN model for solving such matrix equations. It was necessary to ask some questions to find some properties, and this property enables direct application of, and a GNN model is developed. We will analyze in third lecture this.
Is there any other question? Any other questions? If no, then please give big thanks to.
Okay.
Okay, now our next section, afternoon session, Professor Predrag would be teaching DMP inverse, is it? Okay.
Will be DMP, will be GNN for implementation of
okay,
DMP.
GNN, DMP, and some more other things also he would be discussing.
And
Please
if we
start.
have time, I am planning to present some additional results about ZNN.
Okay, go ahead.
Here is result about eigenvalues of DMP inverse. If lambda is eigenvalue of A, then lambda dagger is in eigenvalue of A d dagger, where lambda dagger is 1 by lambda in case if lambda is different than 0, and 0 if lambda is equal to 0. So far I didn't investigate eigenvalues of G inverses in details, but possible that similar property is valid for many classes of G inverses. We can ask Mathematica what will say. I will try first with numerical example in any case. Here is this numerical example, later with symbolic. In any case, I'm not sure what will be. Here is numerical example. We first need to find index. Index is equal to 2. So AK is matrix power of A, 2, A dot A Drazen. And then we will need to compute, after A Drazen, DMP inverse. Drazen inverse is here. Then A DMP is equal to AD dot A dot pseudo inverse of A. We are interested in eigenvalues and of DMP and the relation between eigenvalues of DMP and A. Eigenvalues of A three, two, two, 1, 0, 0. Eigenvalues of DMP of A, it is ADMP in exact form 1, 1 by 1, 1 by 2, 2 times, 1 by 3, and Moore-Penrose of 0 is 0. It is verification. Probably that many classes of G inverses possess this form. I want to see what will be in symbolic matrix case. Matrix in symbolical form. Index here was 1, I think. Requires more time. It is symbolic computation with unevaluated symbol. Then we need DMP as AD dot A dot pseudo inverse of A. Simplify. Without simplify, it will not work. Eigenvalues. Small v, it is one word. Of A. Can we ask numerical values? Some eigenvalues are real numbers, but some eigenvalues are solution of some nonlinear equations. I will try to force Mathematica to compute numerically. I think it will not be possible. I tried this morning. Yes, tried this morning. Cannot obtain. What are eigenvalues of A DMP, of DMP inverse? -1, okay. 1 by -1 is -1, 0. Moore-Penrose, probably reciprocal value of this should be such root. It requires investigation. I tried to force Mathematica to numerical calculation, did not success. Possible that another approach can do this. Now I will show you how to prepare some appropriate numerical examples in your papers which you obtained. We will go to investigate how this example 4.1 has been prepared. This example has been prepared in Mathematica. First, we need the definition of matrix A not constant, polynomial matrix. Obtain such results by on hands is almost impossible. I must split my display in two parts. Here is part for PDF file of results. There is part for numerical experience. Visible in this form. Can be bigger. Visible. Here is definition of matrix A investigated in example 4.1. First, DMP inverse is computed. Here is. We spoke that this part A pseudo inverse of A power 3 dot A is aimed to computing Draisian inverse of A. Index of A is equal to 1. Then A, and after that Moore-Penrose inverse of A. We want to simplify, to compute this inverse. Should finish in short time. If we want to put this result in here in LaTeX file, you can use TeXform command of DMP. Only copy paste and will be ready for your LaTeX file. Really simple way to prepare numerical examples and almost error-free. Then here is one representation of DMP inverse. Here are three limit representations of DMP inverse, and we want to verify, to prepare numerical verification of these limit representations. Here is I will try to find epsilon. Here is. This matrix is of order 5 times 5. And then we will follow A dagger, where A dagger, second representation. Want to verify if limit when small parameter epsilon tends to 0 of A power index plus epsilon identity matrix, then inverse A, L is here 1, A dagger is equal to DMP inverse. It is theoretical result, and now we want to verify this result in package Mathematica. A much better verification is made, of course, in symbolic case. If you use arbitrary parameter and obtain result, or even 2 parameters, or even bigger dimensions, try with different dimensions. Here we need identity 5 times 5 matrix. We call this matrix I5, identity matrix of order 5. And then we need expression inverse of A, L is equal to 1 plus epsilon. Epsilon we use the symbol from Mathematica, from standard toolbox for from assistant, palette, basic assistant. And here we can find basic symbols. Epsilon is here. If we trace carefully, here will be epsilon. Here is, if you can see such small font. Press and then epsilon will be in our notebook. And we use such an unevaluated symbol epsilon to generate such expression. Inverse of A plus epsilon, identity matrix, times A dagger. Simplify. Without simplify will not work. Will work, but result will be will be huge and finally not. Then we ask limit of this standard function limit in Mathematica to find limiting value of our expression when epsilon tends to 0. Simplify again. In that way, we are able to find limit theoretical result. Expression was unevaluated symbol, and after that we asked limit representation with respect to this unevaluated symbol epsilon. Simplify, of course. And again, we can verify that this matrix is the same as DMP inverse computed according to definition. Other verification, again, symbolic expression with epsilon is generated. Now we use the representation 1, I think. Yes. K is 1. Index is equal to epsilon. Identity matrix of order 5. Dot A, and then pseudo. We can conclude that epsilon is an unevaluated symbol. Looks complicated. Limit. And epsilon tends to 0. Here we ask the difference between DMP computed according to limit representation and the DMP computed according to definition. Surely DMP1 expressions obtained using limiting representation. And both of these representations agree with the theoretical solution. In a similar way, we can verify second. Here is not example about this. Possible, it is possible, it can be done. Here is one example. Imaginary, it is imaginary unit, which means that elements of, and we will try the same to test the limiting representations in Mathematica, which defines such expressions. Matrix rank of A square. Index should be defined first. Drazen inverse. In our case, it is computed in this way because index is 1, A dot Moore-Penrose of A power 3 dot. Now correspond limiting representation using generate this expression with respect to unevaluated parameter epsilon. DMP is computed according to definition, must be the same as DMP1 computed by limiting representation. Difference is equal. We can use tech form. Gradient neural network aimed to computation of this GNN model is defined using representation of the form 7-6. We will A more Penrose A this expression is equal to AK. We can use one A from AK, A dagger A will be A, return back to this part, and again we it will be interesting to investigate, but it will require more time. Here we are interested in GNN model according to topic of our course. Use A power K A dagger as our matrix G. This matrix G is given in right hand side also. And in this way our design is based on equals G, or we can consider equation GAX equals G for G equal to A power K A dagger. Error function will be goal function will be Frobenius norm square of F equals minus gamma derivative of scalar epsilon in front of v of t we have GA because here we GA v of t minus G. Where is minus gamma? Here is one detail more. GA is equal to A power K so here we will have A power K. If you remember, our symbolical matrix had index equal to 1. Constant matrix had index equal to. Using expression A power K pseudo inverse of A dagger. Call of function SVD which we use to compute pseudo inverse. It is A square obtained as product of A by A square, then new product. And here is, it is GA. A square is GA. It is A square because of properties A power K, A dagger A equals. Here we have two inputs, GA and another part with minus. we need to multiply this by positive gamma, then I think here should be only G. Result of this will be, it should be, we should put a square v of t minus g, one level below. Value of this stream, of this connection is g. Then it's time v dot of t, output is v of t, and here we presented current value. Okay, we can open today's more. Then we can define all necessary parameters and evaluate. I'm trying to open. I will put this expression down. Stream is only g equals a squared Born-Penrose, and here is 2 minus I can only try shortly with one input. It looks similar as our matrix. Copy. What is with another values? 0 initial state, okay. Gamma minus 6. Here is pseudo inverse. Try. Matrix. What? I think it is the same matrix. Here should be. One by 4 will be finally, according to trajectories, element-wise trajectories of v of t, their equilibrium states. One solution is to increase gamma, another solution is to, increase time interval. Here is 1 by 4 we obtained. So there is one approach based on recurrent neural network, another approach based, and it will be good in your research if you include some examples. Prepared table behavior to equilibrium states is evident, and result here is evident. This term can be considered minus 18, minus 17. Numerically, it is 0. Moreover, we considered another property of DMP based on block representation. Then it was necessary to generate a block matrix with blocks defined in this way. Here is DMP inverse of A, down is DMP inverse of D, M is matrix of this form. AC 0D. Then statement is that DMP of M is given, is the following block form. And in Mathematica was necessary to generate such matrix, matrix with such blocks. Here we used the possibility to work of Mathematica to work with lists. First, we use array flatten, how to say, of block matrix A and A DMP. First 6 columns, and then product A and DMP of A in next 6 columns. Then use another array flatten condition function made from DMP A dot A and DMP. Here columns is aimed to A DMP times A, another 6 times 6 block is aimed to matrix A DMP. And then great tool to define block matrix. For blocks we need frequently, and after that we can investigate properties of this matrix. My goal here was to present you how we can use Mathematica to define tag form is always available and put directly in your paper. If we consider rows, first 6 columns, here is matrix A, here is another, if I remember correctly, A DMP, and so on. And after that we can investigate properties. So, because we have 6 minutes more only, my recommendation, we will continue tomorrow. And now we can spend these 5 minutes for your So if they wait you to ask questions.
Continue.
So most
null space.
so
It means or sometimes range, sometimes null space.
so much generalized inverses. So instead, so it's all interconnected.
Inverse is best and
Yeah.
more
Why
present.
you are using this outer inverse
1-3 inverse is useful. 1-3
application?
inverse because 1-3 inverse is behind 1-3 inverse.
Mm.
And finally, if solution is least square, it is generated by least square solution. 1-4 inverses are aimed to 2 inverses can find some applications in solving differential equations and such many outer inverses because well-known generalized inverses. One of them is DMP inverse, another one is core
Or control our movements,
definitely.
but
In
we
solving
haven't.
equations, solving matrix equations, linear, in all fields of linear algebra.
So
Of course.
that's what I was asking. Where do we actually use the Dresdenization?
Dresden inverse is also related with some minimum constrained matrix equations with range. Dresden inverse is one of basic inverses applicable in solving such constrained maybe. It is always possible to find the appropriate matrix equation and appropriate linear system, which is we can prepare some constraints such that obtain solution using Dresden inverse and using or using Murpenau's inverse.
And in that case, we can find this 1 inverse, 1-2 inverse. Because all these 4 conditions of Moore-Penrose inverse, sometimes it is difficult. Yes?
Murpenau's inverse is best.
Is best, but in application point of view, difficult.
Yes, if
So
finally
inverse is 1-2, 1-3, 1-4 inverse.
Uh-huh.
Moore-Penrose inverse is very much powerful, and you have the strong stability. And
Here is one
always it is
inverse.
not possible.
One inverse can be used, arbitrary one inverse.
Yes.
But which inverse
Is there any application towards graph, this Dresden inverse and this generalized inverse? Graph theory?
in graph theory?
Yeah.
Incidence matrix
Incidence matrix.
can be considered Laplace matrix
Laplace
from
matrix.
graph theory, and
Yeah.
people in matrix investigated.
There are nice connection between graphs and this generalized inverse. So in that sense, to analyze the properties of graphs, sometimes you can see the generalized inverse. Is there any other questions? So if you have,
Are we going to talk about the Lyapunov stability of ZNN models?
About
The
Lyapunov stability.
Lyapunov stability, GNN and ZNN consider Lyapunov stability.
and
It continuous time models is based on Lyapunov function candidate and Lyapunov stability. We used in one of our proofs Lyapunov candidate and Lyapunov stability to verify. Typically, all verifications of convergence in continuous time model is based on Lyapunov stability.
and are we going to check some finite time convergence model and their finite time convergence?
Time activation function, we can obtain finite time convergence. I will present several finite time models next 2 days.
Like FTZNN or VFTZNN? we can see the proofs.
ZNN mainly, but sometimes in GNN can be considered such activation. Only with the nonlinear activation we can achieve finite time convergence. Without
So, okay, let's give big thanks to Professor Predrag.
thank you.
That is nice lecture. And the singular value decompositions, okay, and its a connection to the eigenvalues, okay, yes or no? You can understand better way, is not it? No matrix, eigenvalues, singular values. If you don't know, you can connect how to find the singular values from eigenvalues, yes or no? So, in our last class we discussed about the proof of singular value decomposition, okay. Like singular values, like eigenvalues, singular values also very sensitive if they are very close to 0. You can see here is an example we have seen. If the matrix you have 1 by 60,000, okay, the small change in the A, originally with a 0 in the 4-1 position. So, earlier it was 0. So, now we have changed say 1 by 60,000, okay, creates a much larger effect in the eigenvalues of A. Okay, the eigenvalues of A were all 0. This were all 0, lambda equal to 0. Now after changing a slight in the 0 entry with this, 0 entry, the eigenvalue moved to 4 points on a circle in the complex plane, center at the origin with the radius 1 by 10. Now the singular values you can see, these are the, if we do calculate this ATA and this is AAT and this is a normal matrix, and you find all the eigenvalues of this and take the square root and you will find all the singular values, yes or no? Okay? And these singular vectors remain essentially unchanged. The fourth piece of the singular value decomposition is this one. This is sigma 4, U4 and V4T would be like this, okay, because this is sigma 4 is very small quantity, mostly 0 except for the new small entry, okay. So, just you find the eigenvalues of this and you have this matrix is this, okay, and you just take the A transpose A and take the eigenvalue and you take the square root of this, yes or no? So, this is true for any non-square matrix. If you have over-determined, under-determined or singular matrix, always you can find the singular values, but this is not the case of eigenvalues. For eigenvalue of a matrix you can find if it is square matrix, otherwise no, okay. Singular vectors A and the eigenvectors of this matrix A S equal to A transpose A. So, singular vectors is nothing but the eigenvectors of this transpose matrix A transpose A, okay. So, when you get the eigenvalue and then you are finding eigenvector of that matrix, here instead of A you are finding the eigenvector of A transpose A. So, if you find the eigenvector of this A transpose A, and then that means you are finding the singular vector of that matrix A. That means basically you are finding the eigenvalues and the eigenvector of the matrix A transpose, okay. So, everything you are doing same, whatever you are finding eigenvalues and the eigenvector of a matrix, square matrix, once you do the transformation in this one and it would be square matrix. So, you can find eigenvalues and eigenvectors, okay. So, likewise here, so that the right singular vectors A B I equal to sigma I U I, okay, and the Q I these are the eigenvectors of this A transpose A matrix. The eigenvalue lambda I of S are exactly sigma I square, where sigma I are the singular values of A. If the rank of this matrix is R, then the SVD produces a beautiful parallel orthonormal sets. These are, as I told you in my last class, they generate 4 fundamental subspaces. Okay, 4 fundamental subspaces. Here is Qi orthonormal eigenvectors of S A transpose, and this is called sometimes it is called a singular vectors, and this Vi is the right singular vectors of A equal to Qi, you know, and this Ui is the left singular vectors. I have already discussed how to find this Ui. If lambda is repeated eigenvalues of S, we must find 2 orthonormal eigenvectors corresponding to it. Okay, we must find 2 orthonormal eigenvectors corresponding to it if lambda is a repeated eigenvalue. Okay, and we want to understand how SVD successively pick up rank 1 term sigma 1 U1 B transport, and this etc. each order by the importance. Basically, as we have seen our singular value decomposition, we are generating rank 1 perturbation, rank 1 matrices. Okay, A equal to U sigma V transpose. Say A is R, say n cross m, and this would be n cross n, and this is n cross m, and this one is m cross n, isn't it? And if R is the rank of this matrix, R is the rank of this matrix A, and say R is the less than minimum of Mn. Okay? Either it is overdetermined or underdetermined system, and then you are taking this A equal to this U1, and this is a Un, and this is sigma 1, and this would be up to sigma R, and this is 0, 0, 0, 0, and this is the size of n cross m, and this is a matrix V1 transpose, V2 transpose, and so on, Vm transpose. Okay. So from here you are getting a matrix equal to summation of R. This is what it is telling. This means this is sigma 1 U1 V1 transpose plus sigma 2 U2 V2 transpose, and so on, sigma R VR UR VR transpose. This is each one, this is rank 1 matrix 1 cross 1, this is also 1 cross 1, and this is 1 cross 1 matrix. Okay. So we can get 1 cross 1 matrix in each cases, each order by the importance of this. Okay. The largest eigenvalue, we just find this one, this is S equal to ATA, largest eigenvalue lambda 1 of S. We just find this, the maximum of X norm square. And this norm, you can take this 2 norm, Euclidean norm, and sigma 1 is nothing but this is square root of lambda 1. The sig is first singular value, the maximum singular value, you are getting this lambda 1 square root. And since the matrix is a symmetric and positive definite, so all the eigenvalues would be positive and non-zero. Okay. So in that way you can find. Again, the maximizing vector is x equal to V1 and a V1 equal to sigma 1 U1. This is how SVD identifies the dominant direction in which Ax picking the vector V1 along which A stretches the most. Similarly, you can find the lambda 2. Lambda 2 is the same variational approach used to find the lambda 1 sigma 1 also applies to the second eigenvalues and the singular values. So here is lambda 2, this is maximum of x which is perpendicular to q1, okay, x not equal to 0, xt s x xt x, and this is winning x is q2. So likewise you have this lambda 2 and x2, and here x is perpendicular to q1. We find that lambda 1 equal to sigma 1 square and lambda 2 equal to sigma 2 square. And this is and the relation between the Rayleigh equations and the eigenvalues. As you have seen this eigenvalues and the singular values relation, here the begin with the Rayleigh equations. This is called the Rayleigh equations, and this is the denominator is not equal to 0. And okay, to find the x that maximizes Rx, we compute the gradient of Rx and set up the derivative. Okay. This means the maximizing x is an eigenvector of S, and Rx reaches its maximum at the largest eigenvalues. So, if you take this Rayleigh equations concept, you will be getting the maximum at the largest eigenvalue lambda 1. Now, you observe that you have this Ax, and you can write in the inner product form, okay, this x transpose or x transpose x, then that you can find xt as x square root. This is a norm and the inner product, that is a relation. This is equal to x norm equal to xx square root. Okay. That we have done. X, you just put ax transpose and this x, and you take the square root, and ata equal to s, and then you set. So, maximizing the same as maximizing this one. Therefore, the maximizer equal to x equal to b1. For equation 9 is the equation sigma 1 equal to 2. So, all the game is to find the singular values. We now explain why Q2 are the solution because they are orthogonal to Q1. They lie in the subspace orthogonal to the top singular vectors, and choose any orthogonal matrix Q1 such that Q1 equal to this one. Okay, because you can always get in this form lambda 1 Wt and this one, because this is a S is a SQ. You can write this where Q1 Qn are the orthonormal vectors. And if this is the eigenvector, then you can write its corresponding eigenvalue lambda 1 Q1 and so on you can write. And if you do write in the matrix form, and then you can get Q1 transpose SQ1, and you will get this matrix, and this is a symmetric matrix, and this S is a symmetric, you can write in this form. Okay. So, because S is symmetric, and so is this is a Q1 SQ1, which forces W equal to 0, and then you get this lambda 1 Sn minus 1. So, this is the diagonal form you have. This isolates Sn minus 1 as a smaller symmetric matrix, in which we can now solve its eigenvalues lambda 2 and the eigenvectors of this. So, this is the way we can extract the eigenvalues and the eigenvectors of this, because once you got lambda 1 for this matrix, because this is similar to this matrix right hand side, and you got this lambda 1. Okay. Because symmetric matrix is always diagonalizable, and you got this eigenvalue, and similarly you can find the second eigenvalues of you can, without loss of generality, you can find Sn minus 1 is of this form, diagonal form, and you can find all the eigenvalues of this. We can now repeat this process. As I told you, you just repeat the process, choose the x orthogonal to lambda j. So, you do the iterative inductive construction, yields the complete orthonormal eigenbasis and the eigenvalues of this, providing the spectral theorem. Every symmetric matrix S can be diagonalized. So, every symmetric matrix in the previous classes, I told you that you can apply source decomposition, that every symmetric matrix. So, if A is R n cross n, this you can write U equal to U, this transpose T and U transpose. Okay, where T is a quasi upper triangular matrix. If it is a real matrix, then this should be like 1 by 1 or 2 by 2 mat. And if A is symmetric, then you apply A equal to AT, and both sides UT U transpose. This is equal, and this is called quasi upper triangular matrix. Quasi. We have seen A equal to CN cross N. Then you have this A equal to or T equal to unitary matrix. Okay, unitary matrix. Okay. So this is called a you have this S is a similar to diagonal matrix, where Q is orthogonal matrix. Like if it is a real matrix, for this is real matrix, and this is for complex matrix. U transpose, this is U, T transpose, okay, and this is U transpose. T transpose, and again you multiply U transpose, you will get T equal to T transpose, okay. Triangular matrix which is symmetric is diagonal. So T is diagonal. This implies T. So you can prove like this. We computed in practice, and how does this relate to the geometry of an ellipse and the compression of I A B I equal to sigma I ui. This is coming like eigenvectors A B I equal to lambda I B I. The singular value sigma I are square root of, as discussed. This is because symmetric matrices are stable and well behaved. So since we are calculating singular values via symmetric matrix, so it would be always stable. Of the symmetric matrix in general it is stable, but sometimes it is not stable, as you have seen example of Hilbert matrix. These are the symmetric exceptional where the stability is missing, for the case of Hilbert matrix. Okay, eigenvalues for the symmetric matrix, but in general we can find the stable matrix because we are finding the eigenvalues of the symmetric matrix. Once you know the eigenvalues of the matrix, that means, so this is it. Just you find the eigenvalues of this and left and right eigenvalue. Yes, explicitly can expensive and numerically unstable, as I told you before that. So instead of forming S directly, we form with A using the technique that preserves its singular values. So sometimes it is very close to each other. If they are very close to each other, and this would be very difficult to compare. The same eigenvalue. This is done by similarity transformation. So what you do? Now generally for computing the eigen, you get this ST, SQ, and you can get also upper triangular matrix by using eigenvalues, and because S is symmetric, S this is also symmetric. In particular, we aim to choose Q so that Q transpose SQ is tridiagonal, a symmetric matrix with non-zero entries only on the main diagonal and the two adjacent diagonal, to get the matrix to upper triangular matrix by using similarity transformation. Okay, by reflectors or Gibbons transformation. Reflectors in other way you tell as a Hausdorff transformation, and rotators you just use this Gibbons rotation. So you can get the similarity transformation, symmetric matrix also ill condition. Okay, so that's why you use the similarity transformation. If you use the similarity transformation, you can get the sparse matrix at the right hand side, as I told you. If you have 2 by 2 matrix, 4 by 4 matrix, you just make the reflector upper triangular you can make, and sometimes you can make it to Heisenberg form. Okay. Yeah, you just see this here. What is the SPD? Analog this for A dash equal to this one, and this, then this transpose, this is similar to this because this is the A dash transpose and A transpose. We have taken this, and finally you will be getting Q2 transpose and Q2. You have this one. Okay, that means the eigenvalues of this S is nothing but the eigenvalue of this. So earlier you have taken already this one, is not it? You are maintaining similarity transformers. First you have done Q1, then you Q2. Okay. In last class we discussed all this. If it is symmetric matrix, if it is symmetric bidiagonal matrix, non-zero this entries only on the main diagonal and the first super diagonal. So if it is so, then you can get the Q1 T and A Q2 equal bidiagonal matrix. And this matrix you can get the bidiagonal matrix. That means you got the sparse matrix you have. This step is a core part of this practical SVD algorithm. It reduces the complexity of the problem while preserving the structure we care about. So likewise, you can find the singular values of this matrix S, okay, A transpose A, by using the reflectors and the rotators. Okay. So here this reduction beautiful mirror the process symmetric matrices. If a bidiagonal and this bidiagonal, you will get the tridiagonal matrix. If you take the bidiagonal transpose bidiagonal this product, you will get the tridiagonal. So reducing A to bidiagonal form gives this tridiagonal form. Okay. If you transform into bidiagonal and it's a transpose A gives the tridiagonal form. Another instance of the strong relationship between the SVD and the symmetric eigenvalue problem. Okay. Suppose you have you want to find this suppose you transform into tridiagonal form or bidiagonal matrix into a fully diagonal form omega or sigma lambda or sigma. This requires more advanced iterative techniques including the QR algorithm for eigenvalues and this divide and conquer methods and the implicit shift QR for the faster convergence of the eigenvalues. The difficulty of this problem is to find this determinant of S minus lambda I. This is a degree n polynomial where n might be in the hundred or thousands. No closed form solution exists for large n, but modern algorithm approach the diagonal from the iterative and efficiently. So basically what we have this determinant concept you cannot use to find the roots of the polynomials, because in general it is very difficult to find and it is an unstable one. Okay. As I told you, for the rounding error, floating point errors it affects. Okay. So for that what we do, we just apply the QR algorithm and make this similarity transformation, and or sometimes what you do instead of tridiagonal you make into Hessenberg form. And as I told you, if you transform the matrix into Hessenberg form, it will take less cost. The floating point operation you will preserve. Okay. All the eigenvalues is hidden inside the simple commands in the most numerical software. This eigen yes, as I told you, as I have told you to find the eigenvalues in the MATLAB. This is the command eigenvalue of S A equal to U sigma Vt. These functions internally use orthogonal transformation to reduce A or S to bidiagonal or tridiagonal form, then iterate towards the diagonal form. Okay. While we often think SVD as a mysterious black box, the path to computing it's a highly structured. Reduce A to the bidiagonal form using orthogonal matrices. If it is a symmetric matrix, then you can form into bidiagonal form also. I use the iterative method to diagonalize the bidiagonal matrix. The connection to the symmetric eigenvalue problem, this is central, and the stability of the singular values, unlike the potential instability of eigenvalues, makes SVD a powerful and the reliable tool for numerical linear algebra. Okay. So if we repeated QR factorizations and if you follow this, then you can find the singular values in a stable way, and which would be very much reliable in your computational work. Okay. So always you need to find the eigenvalues and the singular values in a stable way. Okay. So basically, if you have any matrix A, then you can make into Heisenberg form, as I told you in my last class. Again, I am repeating. So Heisenberg U form by using reflectors. Okay, reflectors or rotators. Okay, Householder transformation. And I have discussed how to find these reflectors. Okay, how to construct these reflectors. If a matrix X, if a vector X is there, then you can form U and V, and I minus P equal to I minus gamma U transpose. This is your Q, reflectors. Equal. And gamma equal to, you have this gamma equal to 2 U transpose. If U is a unitary matrix, U minus 2 U transpose. Yes. So each time you are constructing this U, and you just see where you need to make this equal to 0. So basically, if you can transform this similarity transformation, the Q1, and you just multiply this matrix here, this you will get this one matrix, say it is a 4 by 4 matrix, and okay, this is a 4 by 4 matrix. And again, since you are maintaining the similarity transformation, you just multiply from the right, and you will get this same without interchanging the zeros of 0 would be remain as it is, only this entity just previously. Okay. So that means if this matrix A is similar to this matrix, eigenvalues of A and eigenvalues of right hand side would be same. U transpose U, and this is U transpose, this one. Yes. No, it would give you 1, and you have this gamma equal to 2. Okay. Clear? So likewise, you will use transpose, and this is Q1 transpose, A Q1, and then again you are multiplying Q2 transpose star this one, and this you would be getting star here. Okay, and this you are getting 0, and this is star. This Heisenberg matrix. Then this is the main idea to get this Heisenberg form. As I told you that you cannot apply diagonal. To minimize your cost, you just transfer that matrix into tridiagonal form or bidiagonal form. As you have seen, this is the symmetric matrix. Okay, and you are finding the singular value of a matrix. That means you know how to find the singular value of the matrix. So if it is a symmetric matrix, then you perform the same into the Heisenberg form. So this is already you are maintaining similarity to similar. Okay, this is equal to Heisenberg. And this Heisenberg form, there are two types. One of the entries in this are 0. Say if any of this entries, say here, okay, this diagram 0, and here 0 S2. Here is some entry, say. So if you have any of the 0 in the subdiagonal entries, if it is 0, you can make into 2 Heisenberg form, H1 and H2. This is also H1, this is also a Heisenberg form, and this below part is also in the Heisenberg form. Understood my point? So once you got this 2 Heisenberg form, then you can extract it is a smaller problem. Instead of bigger problem, it would be just take H1 is a I by I matrix, say, N1 by N1, say the size of this N1, this N1, and this is say N2. Okay, N1 plus N2 equal to N, say. This is n1 by n, and this is n2. So n1 plus n2 equal to, this is equal to n. Clear? If we have a big matrix, okay, and you transfer into Hessenberg form, and if its subdiagonal entries, if any of the subdiagonal entries is 0, one of the entries is 0, you make this partition. That means you would be getting block upper Hessenberg form with the diagonals are in the block form. You know it. So you just take the perform the H1 you just take, and H2 you just take separately. You find the eigenvalues of this matrix. This is H1, and find the eigenvalues of this lambda of H2, and you make the union, because block diagonal this union of this eigenvalues of H1 and the eigenvalue of H2, you got this. This is for the properly Hessenberg. If any of the entries is 0, so you make into two parts. The smaller problem you individually you perform the QR algorithm, get the eigenvalues for this, and you get the eigenvalues for this one. So things should be as it is. If it is not, that means none of the entries are 0, then you perform directly to that matrix, because you cannot break into two block diagonal form. Okay. This SBD factors matrix A into A is, as you have seen, and this square the singular values, these are the non-zero eigenvalues of both A transpose A and A transpose. Either you take A transpose or A. And the orthonormal columns of U and V are the eigenvectors of this, as you have seen, and the columns, these are the orthonormal basis. This is fundamental subspaces, the column space of A and null space of A transpose from U, and row and null space. This basis diagonalizes the matrix, okay, ABI equal to sigma I UI, and which gives AB equal to U sigma I. I varies from 1 to R or I varies. And as I discussed, this you are getting this rank 1 matrices each of this, okay. And if the rank of this matrix is R, then you can get till this R terms, okay, and this sigma 1 sigma R you will be getting, okay. If it is a n by m matrix and if its rank is R, then only you will get the R terms. This two would be as it is, and this is sometimes is called a condensed form of SBD. So that means you are removing all the zeros, and you are getting A equal to UR sigma R VR transpose, okay, and UR is n by R and sigma is R by R, okay, and this would be R by M, okay. So likewise you are reducing and the compressing your data. Orthogonal columns, orthonormal columns you are getting, and the triangular columns also you can, where do the rank, the pivots and the singular values of A come into the picture. These three factorizations are basic to the linear algebra, pure or applied. This means basically you need to either a matrix to triangularize, or you just make the orthonormal columns or orthogonal columns. Basically, for the computational point of view, you need this kind of columns, because the norms would be invariant under 2 norm or the Frobenius norm for finding the least square application, okay. Because any matrix, if you transfer into orthogonalizing, or you are unitarily similar to triangular form, in that case you are making a matrix to sparse, and then you can apply the gradient or Lagrange method, you can find the optimal solution. So basically we have this one you have, and then you have the QR, also you have the LU decomposition you have, and this you have also this LDU with the diagonals are 1 and L and U, the pivots DI are in D. So, this already we have discussed in our lectures, that there are various matrix decompositions in the linear algebra. Okay. You have seen singular value decomposition, also you have got the source decompositions, the triangularizations. One of these are the triangularizations. So, any matrix, complex matrix you can triangularize. Also any complex matrix or the real matrix, you can have this, either it is a U and V are orthogonal when A is a real matrix, and this U and V are unitary if it is a complex matrix. Okay. And this Gram-Schmidt orthogonalizations also we have seen A equal to QR. Okay. Gram-Schmidt also we have seen by reflectors QR, also by using the rotators also QR we have seen, and also you have seen A equal to LU decom, and you have seen LDB also, where the ones are in the unit lower triangular matrix. Okay. And also you have these properties, you know that the determinant of A is the equal to product of sigma i's, and this is product of di, where di when A is a because here is the product of eigenvalues you have. If it is a symmetric matrix, then sigma I and the lambda I would remain same. And if it is symmetric, that means ATA, it is a symmetric positive definite, and this these are the that's why we have taken the absolute value if A is a symmetric. The symmetric matrix you have this sigma i's are this is equal to lambda I ATA, and this is square root. Okay. Got my point? So, if A is symmetric, then lambda I equal to sigma I, the positive part of this, if A is symmetric, is not it? If A is symmetric, A equal to AT, then you have sigma I equal to lambda I AT or A square, and this is square. Okay. This is whole square, and this is square root, and this is positive eigenvalue you just take. This is sigma i's, this one. Okay. So, this is nice relation between the singular values and the eigenvalues. If you know eigenvalues, you know singular values. This, that's why here is the product of the singular values. We in general we know that this is the product of eigenvalues, but if the matrix is symmetric, it is same as the product of singular values, or it is the product of eigenvalues. And you know how to get this singular value. This is a norm, as I told you, the operator norm would give you the sigma 1 if you just divide this and take the maximum of x, because this is coming from here. You have the SVT A equal to U sigma Vt, and you just take this Qx, this is norm of x multiplying the orthogonal matrix, does not change the length, as I told you. This is Q is the orthogonal matrix, and x, and you take the norm equal to this one. This is invariant under norm, okay, either 2 norm or the Frobenius norm you have, and this you just put the inner product, that is x norm square equal to xx square root, and x is nothing but it is qx, okay, and you just do this, and this is orthogonal, this xtx, this is equal to 0, okay, and this applies to q equal to u and q equal to vt, v transpose in between the orthogonal diagonal matrix sigma, and you get this u sigma v transpose x, and you can take u outside, that would be 1, because u is a orthogonal matrix, sigma v transpose, and this sigma contains what? Singular values and v transpose x, okay. But this sigma 1 is the maximum of the singular values, you know. If you take the sigma 1 and you take the sigma 1, and that would be the largest singular values, because either you take the 2 norm or the Frobenius norm of this matrix, because you are taking sigma v transpose, and this is x v transpose x, yes or no? What sigma contains? Sigma contains this sigma 1 and this is sigma r, and the rest are 0. If the rank of the matrix is R, you get all the R singular values where sigma 1 greater than equal to sigma 2 and so on, sigma r which is strictly greater than 0 because this is non-zero singular values. And from here you can see that, and these are the relation, okay, sigma 1 up to sigma 2. So if this is a maximum one, and so obviously this less than equal to sigma 1 and this one. This is 2 norm of sigma 1. This always or you take this 2 norm equal to this is sigma 1, that means maximum one you just take, or if you are taking the Frobenius norm, that would be sigma I square. I varies from 1 to r, and this is square root. So this is obviously, if it is r sigma 1 you are replacing, this you can take r times say sigma 1, is not it? Each time you are taking say sigma 1, sigma 2, sigma, this is r number is r, so obviously this is always bigger than this sigma 1. Or you take the maximum one, always you will get the less than or equal to sigma 1. This maximum of sigma I, 1 less than equal to I less than equal to r, and this is maximum is sigma 1. Maximum is sigma 1. So you can take this one, sigma 1 maximum. So likewise, you just divide this, and this you take the maximum, because since x is a singular values, so you always have non-zero. Okay, if it is non-zero, then you just take the supremum, and then you will get the sigma 1. This is this you will get ax norm of x, and you take the maximum, okay, and this would be less than equal to sigma 1. This one you got. So reverse way you can also see this directly. You have sigma I ui you have, you take the norm both sides, okay. This is sigma I ui, okay. Yes, this u1 you got sigma 1 u1 because maximum this one you have, and similarly you can find for the reverse way maximum of x norm if this matrix has a rank R. So any vector you can write in the linear combination of this vector because you have this. Okay, so here you have this. So eigenvalue always is less than equal to sigma 1. Okay, the absolute value of this is always less than equal to sigma. Also apply this unit vector x. Now Ax is the first column of A, then this condition will satisfy. Because the right hand side you have this, all these diagonals are sigma 1, sigma 2 up to sigma r, and the left hand side you have this ij. So here you have seen maximum 2 norm of a matrix. This is equal to sigma 1. And if you find the Frobenius norm of matrix, this is sum of square root of and the square root of all the singular values, you can get the Frobenius norm of this. X equal to b, and this MATLAB wants if this condition number is large. As I told you in my previous class, previous class, that the condition number you can find using singular values. Okay, and this A inverse norm. Yes or no? And this is a 2 norm you can find this K2A, this norm 2, this is sigma 1, and this is A inverse norm 2 maximum. If the rank of this matrix is R, that means this is sigma 2, they like the sigma R. This is strictly greater than 0, and this one is maximum singular value, and this not non-singular, then you have this K2A equal to A norm 2, and instead of inverse, because it is a inverse. If it is pseudo inverse, also you have this, that is sigma 1, this is 2 norm, and pseudo inverse, as you know that A equal transpose inverse, and this is sigma plus, and this is U inverse. Okay, this is V and sigma plus and U transpose. Yes or no? This. Now A plus you have, this is matrix B, and this sigma plus means this is 1 by sigma 1 and this is 1 by sigma. This means the maximum singular values of this A plus, here the maximum singular value is this, because sigma 1 was the maximum, but its reciprocal would be minimum. So maximum would be 1 by sigma. This is sigma 1, and this maximum singular value of this 1 by sigma r. Okay, this is sigma 1 divided by sigma r, minimum value. So this is your condition number of a matrix. Okay. So if you know how to find the sigma by sigma, meaning governs the round of errors in solving Ax equal to b. And MATLAB warns you, if this condition number is large, you go and increase the size of the matrix, their condition number gradually increasing. Or in other way, you just compute their singular values, and you do compute sigma max by sigma minimum, calculate by your hand if it is a small matrix. If it is a big matrix, you cannot find, you have to take the help, and it should not be unstable. Okay. Okay. I have shown you how to find this and the roots. You just use the similarity transformation by using reflectors or rotators. Okay. समझ में आया? Solve X equal to B and sigma max minimum if it is the condition number is very high. Okay. In case of matrices. But this is a operator norm, sometimes it is called, but it is a finite or norm linear space to norm linear space. This operator T norm equal to supremum of norm of X. If the norm properties you know, and yes, and in matrix case, it is coming this value sigma 1, or V to W, then you can have this connected to the singular values of this matrix. Equation, linear systems of equations, is not it. Then you compute the singular values, and you know, if you know how to compute the eigenvalue while solving this equation. Okay. And also you know that this LU decomposition is unstable sometimes. That examples I have given various examples. So if condition number is very, you just use other algorithms like your algorithm to solve your problems. Yes, clear? Any question? Okay. As I told you in my last class, that the matrix, most important algorithm in eigenvalue computation. However, it is applied to dense and matrices only. It is applied to dense matrix. Why it is dense? When the eigenvalues are very, very, very close to a good result, that means your matrix is dense. In other way, ill conditioning, you are dense. That means their eigenvalues are very, very close to each other. Computing eigenvalues is not it is easy to find the eigenvalue of that matrix. Okay. And if you want to know the behavior of the matrix, that means you will change that matrix in the epsilon neighborhood. Okay, it's graph, and you have to understand that in a epsilon change, okay, in what the behavior of the eigenvalues. That way you can study. Otherwise, you cannot study this. Suppose you have a dense matrix here. You want to study the behavior of this matrix. What you will do? You will do a sensitivity analysis. So delta A is very, very small, less than equal to epsilon psi. You are finding this, these are the, say, this matrix domain here is there. You are changing this matrix in the epsilon domain. Behavior of these eigenvalues, and you do small change here, and now you need to know what is the behavior of this change matrix. Then you compare original matrix to this matrix, then you can study the sensitivity analysis of large change. Okay. So what do you study here? You will find all these eigenvalues of A plus delta A. Okay. A plus delta A. You collect all such eigenvalues, lambda will lie in the epsilon less than or equal to epsilon. That means you may have the infinitely many such eigenvalues, because in the epsilon neighborhood it is rotating, is not it? Yes, because you are changing in the epsilon neighborhood, and there are many such delta A you will find, many such delta A you will find whose norm is less than or equal to epsilon. So you collect the eigen change, because whole idea is to know after a slight change, okay, the original behavior of this eigenvalue, and this after small change the behavior of them, and this is called gamma of lambda of A plus delta A, eigenvalues of all such matrices, and you take the union where delta A not less than or equal to epsilon. Understood what I am going to show this? That means in a small neighborhood it's called pseudo spectra. Pseudo spectra, spectra से मतलब कि you will pseudo spectra. Matrix A, pseudo spectra of the matrix A. Understood my problem in a infinite small many change of this, because the matrix is very ill conditioned. If you do small change, it is large change. So that's why if you want to know the behavior of that matrix in a epsilon neighborhood, okay, then you can pick the problem where so this kind of problem, say for example, if you have differential equation, there are two types of differential equation. If a differential equation you discretize, you will get this eigenvalue for as I x dot equal to a x t e to the power lambda a something you are getting. If a is diagonalizable, you make in the matrix form, and you just take the norm both sides, maximize, you will get half plane, it will converge. Yes or no? Because when n goes to infinity, e to the power lambda 1 minus I lambda 2, is not it? It is drastically tending, n goes to infinity, it will go to 0. So if the matrix is diagonalizable, if it is stiff differential equation, you will be getting a matrix equation, but during that time you, because eigenvalue concept won't give you the correct result. You might have thinking that okay, eigenvalue I know, and just find this, it will give you the wrong result, because the matrix you can put in the Google stiff differential equation, how to solve this, and there is one book is called Spectra and Pseudo Spectra by Ellen Trefethen. It's a big book, and it talks about the eigenvalues and its behavior, especially when matrix everybody study. It is Ellen Trefethen. Okay, it is a big matrix. You can find all the worst problems जहाँ पे problematic होता है, वो problems you will get all this, है ना, are very dense. Okay. The QR algorithm consists of two separate stages. First, by means of similarity transformation, the orthogonal matrix transformed in a finite number of steps to Heisenberg form. In the Hermitian symmetric case, to the real tridiagonal form. So in the two states, you get the Heisenberg form, or if it is a Hermitian or symmetric, you will get the real tridiagonal form. Okay. The first stage of the algorithm prepares its second stage. The actual QR iterations that are applied to the Heisenberg form or tridiagonal form. The overall complexity of the algorithm is order of n cube, which as we will see is not entirely trivial to obtain. So, this is the order of n cube when you get the Hessenberg form by using the similarity transformations. Okay. The major limitation of the QR algorithm is that already first stage usually generates the complete fill in for the general sparse matrices. It can therefore not be applied to the large sparse matrices simply because of excessive memory requirements. On the other hand, the QR algorithm computes all eigenvalues, which is rarely desired in the sparse matrix computations anyway. So, generally QR algorithm is already in the first stage generates if a matrix A you have, then you can find, you can apply the QR, that would be a matrix that would be good for this in terms of the cost, the flops, and numerically stable. The treatment of the QR algorithm in this large scale eigenvalue computation is justified in two respects. First, there are of course large or even huge dense eigenvalue problems. Second, the QR algorithm is employed in most other algorithms to solve the small auxiliary eigenvalue problems. Okay. This QR algorithm is very helpful to get all the eigenvalues, but it is not like that. For all the problems you can find the eigenvalues in the stable way. There are problems where you will this algorithm won't give you the right result. I will show you some examples how this QR algorithm performs. As I discuss you how this QR factorization works, the first you form this the QR factorization, and then -1 QK, and this matrix is always similar to each other. Okay. So, in my last discussion we have done that if A is a matrix A you have, then you make into QR. Okay. And then you set say A1, this is R into Q. Okay. And then again you make the QR factorization of this. That means if you have matrix A1 equal to RQ, you have then you have this say A2 equal to Q1 R1. Okay. And then you can check this AK. Likewise, AK you will get QK minus 1, RK minus 1. Okay. And that means AK minus 1 equal to QK minus 2, RK minus 2, and this AK and AK minus 1 is similar. Yes or no? This is the way they have shown this AK equal to RK QK after you just submit this, and then you have the previous step, you can find the QK star, this AK minus 1, that would be RK, and then you have this AK and this one is similar. That means if you maintain the similarity transformation at the end, AK minus 1 are unitary similar, the matrix sequence AK converges under the certain assumption towards an upper triangular matrix or Hessenberg form. This is what we have this. The algorithm computes the upper triangular matrix T and a unitary matrix such that A equal to UT U star. This is called Schurz decomposition, as I told you. The QR factorization and AK equal to AK minus 1 equal to QKRK. That means you are setting this A0 equal to A, and this that means K equal to 1 and A0 you are getting this Q1 and R1. And same thing you just update this AK equal to RK, just you write in the reverse way. That means RK and UK you have done. And again you make the QR factorization of this. Okay. QR factorization. So, likewise update the unitary and set this, you will finally will be getting some, you can number them as that, this one. Suppose you are they are well separated, say for example eigenvalues of the matrices, they are not dense. If they are very dense, then convergence would be problem. As I told you that this division you can see near to linear, and if you go K goes to infinity and you won't get. even 10,000 years if you calculate this, you won't converge, is not it? If they are very close to each other, that if they are very close to each other, that means they are very dense, that means no method will work due to this. If they are well separated, then k goes to infinity, this will go to 0 when I greater than 0. That might be. So, here you will get, and finally you would be getting this similarity transformation like this, ak qk minus 1 this, and this ak minus 1 again this part, okay, and again ak minus 2, you can expand this, and finally you would be getting a0, and that means all matrices, they are similar to the original matrix, is not it? This is ak minus 1, first ak minus 1, you just replace ak minus 1 with this, qk minus 1, ak minus 2 and qk minus 1. Likewise, you go up to a naught. So, finally, you would be getting, and they are similar. So, whatever you are doing, the QR factorization and the similarity transformation, if you maintain, that means you will get the similarity. Now, same assumption on the eigenvalues, the sequence AK converges to an upper triangular matrix and UK converges to the matrix of source vector. So, if you go to MATLAB, you just perform this programming, you just take the MATLAB convergence rate, we construct say 4 by 4 matrix, okay, and the matrix A0 is formed via similarity transformation of the diagonal matrix. Say you take the diagonal matrix and you maintain the similarity transformation, okay, and then you perform this S equal to random matrix this, and you can take the shift also is 0.5, and then you can perform QR factorization, QR equal to QR, I varies from 1 to 20, and then again you just take it in the reverse way, R star Q, okay, every time you are doing, I varies from 1 to 20, and then later on you will see how this convergence is happening. So, here I have done say, for example, we have taken this steps, and so A0, whatever A0, that means your original matrix you have, and this the first iteration you have done. What is this matrix looks like, just you see. As you go and increase this is sometimes this looks like the matrix is a not Heisenberg form, and still you need to find the eigenvalues of this matrix, because we need to make this entry to be equal to 0, and you make a partition, and this last entry would be the eigenvalue. Okay. So, now you see this how the changing this 0. This matrix is going to towards 0. This minus 0.01 in the second iteration you see the minus 0.2. In third iteration and successively you see this one, and this is increasing, and 2.1, 3.7175, now it is 2.1396. Okay. And the other entries are also changing, see. And this 0.2 and now it is changing to 0.3, minus 0.3, and it is going towards 0. Okay. As you know that the matrix, if this is equal to 0, make the partition this, and you will get this last eigenvalue. And now you see this is completely, this is 0.0605, 0.3, and this part, because you need to maintain the this part is going to 0, see 0.3. This is big number because we have to extract this, because this can never be 0. If it is 0, then how will find the eigenvalue? Because the last entry would be the eigenvalues of this matrix. Now, as you go and increase, number of iterations, if you take AK equal to QK, RK, AK and QK star, and this you see 7.5547 minus 0.4, and this is minus 3775104. Okay, clear? And this is changing, not changing. This is the positive number. Okay, and you see again this is 0.5. because all this time you will see this part is going towards 0, okay, and successively these numbers are very, and this is going towards the Hessenberg form, is not it? You see the first, this one, if you take, this is, and this portion is very bigger, okay, is not it? And this also again bigger, this is also bigger, this is bigger, is not it? Now again further you see, this is minus 10, 0.8, minus 0.8, and this is minus 0.5, okay, and this is the whole number. So likewise, if you see this again 11, and this is 1.17, this is minus 5.70. Now in 20th iteration, you see the minus 0.6, minus 10, minus 15, 7, 4, okay, and this number is bigger. You see, this is what you have got this, and this is completely going towards Hessenberg form. Right? The matrix is going towards a Hessenberg form, and this entry is going to 0. That means you make a partition this, and this would be the eigenvalue. Is not it? Now you see the rate of convergence, the previous step and the second step. You just do divide this component wise. The dot slash means you are dividing that matrix component wise. Each entry you are dividing. Then from there you can know what would be the convergence rate. See, if the convergence rate is this 1.0, 0.9. This is because this rate is around this linearity is going, is not it? That's why it is taking big steps. 20 iteration it is taking. The element above and on the diagonals are relatively stable. If we run the same little MATLAB script, but with the initial diagonal matrix D replaced by this, then we obtain this one. Okay, in 19 you will get this form, this one, just by replacing some matrix diagonal, if you change the diagonal entries. So again the eigenvalues are visible on the diagonal A2, the element wise course A2 relative to A3, okay, and then you see this component wise you are just dividing, and you are seeing the what is the rate of change of this eigenvalue. So you notice that previous equation doesn't state the convergence rate for the element at the position 3, 2. 3, 2 position you just see the 3, 2 position. This is this is 3, 2 position. This is 3, 3, 2 position, 0.47. Okay. This small numerical experiments demonstrate that the convergence rate are indeed observed during an actual run of the basic QR algorithm. The conclusion we can draw from our following. What it says? The convergence of the algorithm is slow, because 20 iteration it is taking. Sometimes it may take 50 iterations, sometimes 1000 iteration it may take, because of this dense eigenvalues. In fact, it can be arbitrarily slow if eigenvalues are very close to each other. As I told you, that if eigenvalues are very dense, okay, if the matrix is ill conditioned, they would be dense eigenvalues. In that case, you cannot study, and you have to look about the pseudo spectra by changing a small in the epsilon neighborhood. Then you can understand the behavior of the change of the eigenvalue. Each iteration step requires the computation of the QR factorization of a full n by n matrix. Each single iteration step has a complexity order of n cube. Okay. Even if we assume that the number of steps is proportional to n, the total complexity would be order of n 4. The latter assumption is not even guaranteed as the mentioned in the point 1, because this complexity will increase and it is the order of n 4. We aim to improve both the issues. First, we seek a matrix structure that is preserved by the QR algorithm and that reduces the cost of a single iteration step. But the main idea is to how to reduce the cost. Can we apply some different algorithm instead of QR algorithm when the matrices, when the eigenvalues of the matrices are very dense? Understood my point? If it is not dense, everything will work perfectly. Even LE decomposition work perfectly. Even GNN will work perfectly. When it is Hilbert matrix, the GNN also fails. Also correct. Now, as I told you, that matrix you just make into Hessenberg form to make it faster. The previous example I gave you, direct matrix you are making into tridiagonal form and getting the 0. That is the first part. It took the 20 iteration. So, how to improve that, the cost, or improve our result? You just make into Hessenberg form. As I told you here several times, make the similarity transformation both the sides again and again. That matrix would be Hessenberg form. That you can perform by using rotators and the reflectors. Okay. You know how to find the reflectors and take the first column and apply this I minus 2 QQT, UUT, U equal to x minus y. If x is first column and y would be the norm of x and 0, 0, plus or minus, because it depends on the sign, because you are, when you normalize, it would be minus vector. If it is the same sign, you just take the same sign. So, you perform through a arise similarity transformation, Householder transformation you do, as I told you, and here I am giving the concrete things for the this Hessenberg form. Yeah, how you perform this. This for k equal to 1 to n minus 2, perform this. What you take? X, that the entries. Suppose you work for the first column, you just the first column, you know it. Take the vector x, and with this x, and you make your u or v, whatever it is. Here is v, that means exactly we are getting this u vector, say, and this is sign of this E1, exactly same thing you are getting, v equal to x plus y. So, first you got this u equal to x minus y, and y equal to this is plus or minus norm of x2, and this is 0, 0. This is what you got, and v equal to x plus y, v equal to x plus y, and if it is x plus y, this is x plus x is a vector, this, okay, this is x1 x2 up to xn, and this is plus or minus norm of x2, and this is 0, 0. So, that means if you write in the form of E1, that would be sign of x1, and this sign of x1, this is plus or minus whatever the sign of x, and this is sign of x1. That means x1 is you just take the sign of this entries. If it is plus, you just take the plus. If it is minus, you take the minus. So, likewise, here x equal to E1 is the standard vector. First entry is 1 and the rest entry is 0, and you just perform this expand the hk to size n by n embedding in the identity form. This is qk equal to this ik and 0, 0 hk. If k equal to 1 and the q1 you are getting, this is a 1 and 0, 0, and this is a matrix of size n minus 1 by n minus 1. Understood, my man? As you k equal to 2, that would be, it would be the 2 by 2 identity matrix, and this would be n minus 2 by n minus 2, because the vector size would be decreasing every time. Then you apply the similarity transformation, A equal to Q. This is the formula. What if you can remember this entire things, you can perform this. If it is matrix A and you extract A, x equal to this, that x would be coming in the first column, second column, third column, and all these things. Okay, depending on the diagonals of that matrix should not be hampered, because otherwise upper triangularity will be losing. Okay, if the diagonal would be 0, then because our aim is not to make the diagonal entry be 0, because otherwise how will you find the eigenvalue? Diagonals are the eigenvalues of the matrix. So, you have to keep in mind the x, by choosing x where the diagonals won't get affect, because diagonal से affect होगा तो फिर क्या हो? If you are maintaining the Hessenberg, super diagonals below entries should be equal to 0. This is in your hand how to choose that x. If you are choosing x, the first column enter, then accordingly you would be getting, you are getting n minus 2 size length vector, that means accordingly you will get the cube. That does not matter. it is in your hand to calculate this Q. So, at the end of this process, the matrix A is transferred into upper Heisenberg form and the orthogonal matrix Q satisfies this form. And entire process I have explained you how to get this x, y, u and v. Okay, u equal to x minus y, v equal to x plus y. They are orthogonal. Okay, and with this you are constructing q equal to I minus 2 v v t. Here v v t here I am telling here u u t. So, things are same. So, performing this only n minus 2 Householder reflectors are equal to make this and a Heisenberg form. As I discussed, the resulting Heisenberg matrix is the starting point of the implicit QR algorithm. Each householder transformation affects n minus k by n minus k matrix, because only affects n minus k by n, and the rest of the entry would be as it is. Otherwise, the Heisenberg property would be losing. Okay, because the way we have made this QR factorization, where the structure would get preserved, है ना. कभी कभी ऐसा होता है ना, you have multiplied, जो once you have made the column zeros, it would be disturbed. No, here we are not disturbing. Once we have performed the first row and the first column, it would be remain unchanged in the second iteration. So, likewise we can get the Heisenberg properties every time. Okay. So, if you do perform this, you will get this, this is the flop counts you will get to get the Heisenberg form. Every time you will getting 4 into n minus k whole square, and this is 10 by 3 n cube flops. Okay. So, if you just minutely you will see how to find the q, as I told you to find the QR factorization. If you multiply one way, you will get flops, one flops. Other way, if you multiply, you will get the other flops. You know it. But the multiplication is defined, well defined. Either you take this or this way. Okay, u b transpose b, u b transpose b. 4nm, 2n square m. So, 4nm we prefer. Okay. So, likewise, if you do and you calculate, and this much flops you require, 10 by 3 n cube flops to make into Heisenberg form. Here is one example. You see, suppose A is a matrix is there. Now, you want to perform this Heisenberg form. What I will do? Instead of entire column, you remember when you perform the QR decomposition, we took entire this column. Okay. But here we are taking 1 minus 2. Why? Because this entry we want to make non-zero. ठीक है, अगर ये 0 हो जाएगा तो our Heisenberg property would be losing. We don't want upper triangular, we want Heisenberg. Heisenberg means main diagonal and the super diagonal should be intact. Okay. So, that is why we are taking 1 minus 2. Now, you perform the QR factorization, that is v equal to x plus this vector you just find, like I told you, x plus this one, v equal to x plus y. Okay. X plus y, that is v equal to x plus y. This is this and the e1, because x is vector and this one. That means this is the vector, you have got this one, and just you do some substitute, you will get the v vector. Okay. Now, you perform the this is reflector, h equal to I minus 2 v v t. Okay. Now, you see embedded into the identity matrix. Now, you q equal to 1 0, as we gave the formula, the I k and this one, and now this is the entry you got this. Now, once you got this q, okay, q matrix you got, and this we apply the similarity transform h, and this is our h Heisenberg form, because we do not want this entry to be equal to 0, and this is a 3 by 3 matrix. Only one entry, if it is 0, then entire things would be the Heisenberg form. And for this matrix, you take this matrix and apply the QR algorithm, and what you will get, this entry would be going to 0 when you perform QR algorithm again and again. Okay. As we have seen in the example, that this entry is going towards 0. Once it will go 0, you get this and you get the eigenvalue this one. For getting this eigenvalue, this one should be 0. You know it. Now, here is the step what we did this QR algorithm sometimes you have whatever QR algorithm you have seen without shift. Okay, what the entire process till now, what I told you, the QR algorithm without shift. QR algorithm without shift. Okay, without shift, no shift we have used. Like I told you previously, in power method, you have without shift, inverse shift. Why? If the eigenvalues are very dense to each other, then QR algorithm won't give you the correct result. Got my point? That's why we use shift. And how you pick the shift? If their eigenvalues are very close to each other, you take the external number, any complex number, you subtract this and make the difference. Okay, you have subtracted, and you would be getting, instead of say mu is a shift, and you are calculating a mu I, and apply the QR algorithm to this matrix A minus mu I instead of A. Same process, whatever I discussed. You find the reflectors, you find the rotators, and you perform the Heisenberg form and the similarity transformation. Everything you perform with the shift. Okay. So if the shift is there, then Ax equal to, what is this? Say lambda minus mu x. Ax equal to lambda x. Instead of finding this lambda, you are finding lambda minus mu. Okay? Everything, entire things you are doing. And once you got the lambda minus mu, that means lambda minus mu is the eigenvalue of A minus mu. Just you add it. Whatever x, y, z, whatever you got this at the end, you just mu add. Say gamma you got. That would be the eigenvalue of A. So everything we are doing, and you are subtracting, at the end you are adding. That my point. So main idea is to make the difference, large difference. The matrix eigenvalues are very dense, you maintain the distance. Okay? And if you apply the shift, and you apply that example to this shift, and it would be again faster. Instead of 20 iteration, it would give you result within 5 iterations. Okay? That means it is the faster, if the eigenvalues are close to each other. And some cases, it may not give the right answer. Again, if you have some matrices are ill conditioned, it may not give the right result, because some eigenvalues are separated, some eigenvalues are very close to each other. Okay? Which eigenvalues large distance maintain करता है, and कुछ eigenvalue they are very close to each other. So in that case also, sometimes a shifted algorithm may not work in some problems, some ill conditioned problems. Okay? So here what we are doing, this is start this initialize this A0, that means A matrix you have, and you choose the shift. Okay? How you will pick the shift, that is also important. It is not like that you take any numbers, any complex numbers. And there are various ways to find the shift. Next class I will tell you how to choose the shift. What would be the shift? And here you just choose the shift, and you maintain this AK minus mu k again and again, QK RK. Like you have Q1 R1, then set this R1 Q1, again make a QR factorization, then R2 Q2, then Q3 R3. Likewise, you are performing with this AK minus mu k each time. Okay? So first you perform this shift, and again in the second iteration you have to find the shift again to maintain this similarity. Okay? And then again you update this RK plus UK and plus mu ki. But initially it was RK QK, not shift, but here is shift. We are subtracting and adding. Okay? Every time you are finding the shift. And then you check this convergence. You ask the convergence. If it is no, then next iteration. You go to again choose the shift. Say for example, you have mu1 you have chosen. And you just perform A0 equal to this mu 0, A0 minus mu 0 I, Q0, R0. Then again what you do? You update this. You just same matrix in the reverse way. Multiply. And whatever you have subtracted here, just add it. Got? Now you ask the convergence as per your desired niche. This much tolerance is 10 to the power minus 16 or minus 17, 80, how much you desire. Understood me? Then you set this here. Is this convergence? It is satisfying that you. If it is no, then you perform this. You choose another shift. Okay? Then you choose mu1. Then A1 minus mu1 I equal to Q1 R1. And then you set A2 equal to just reverse R1 Q1 mu1 I. Okay, perform this. Then what will you do? Check the convergence. No. Then next iteration mu2. Likewise, you go. If it is convergent, stop this. समझ में आ गया कि नहीं? This is with shift. If the matrices are very dense, eigenvalues are very close to each other. As you have seen earlier step in case of without shift, lambda k divided lambda k minus 1 divided by lambda k to the power k. If they are very close, k goes to infinity, still you will get 1 instead of 0. Clear? So this is what we have taken this. Here we can QR algorithm with shift input matrix A you have, the tolerance you have given epsilon. This is your tolerance where you want this much accuracy. Maximum iteration A0 you just put A and K goes to 0 and K less than maximum iteration, choose the shift. Here you shift the last entries of the matrix, last entries A n. In the second iteration, A n1, A n2, A n3, last entries. Okay, here is the last entry, each iteration. समझ में आया कि नहीं? Shift. And then you perform AK minus mu k I, you just find the QR factorization. That you know how to find the QR by reflectors, rotators, usually. And again you update it, RK, UK and plus mu k I. So all the off diagonal entries are less than epsilon, break, convergence achieved. Agar off diagonal entries are 0 near to 0, that means you would be getting Heisenberg form. Stop it. क्या समझ में आया? Yes or no? What is the time? Time? Almost time. 5 o'clock? 5:30?
5 almost.
Okay, we'll end this. We'll end this. Understood my point? Try to understand. Difficulty, where is the difficulty? Everybody can solve the well conditioned problem. What is the known algorithm is there? है ना? ठीक है ना? लेकिन nobody is going to where is the difficulties. If we will enter into the difficulties, then you will get a paper in 5 years. Got my point? Yes or no? If this kind of work you will do 5 years, so that much patience you should have. Huh? Is not it? His GNN fails when Hilbert matrix is going on. His GNN fails when Wilkinson matrix is going on. We have checked. Yes or no? So there is a difficulties. So one will take into account where I will work on the ill condition problem. All this algorithm will transfer GNN into ill condition problem as well. You will get all these 300 papers would be with you. Yes, not joking, but difficulties are there. It is not easy that you will get the 300 papers. Okay, maybe in your entire life, 30 papers. It's very, very difficult. Okay. People are very well renowned people are there, entire their life they have only 20, 30 papers. Why? They are not working? They are working. You have seen, many people are there, they have very less paper, but they are working speed up. Okay, these are the problems you can solve. Thank you so much. Okay. I was expecting some question from you. Of course. Please don't close this. Keep live. Yeah. Any questions? Please.
I want to share one my doubt with you, how to say.
Please.
Condition
Please,
number,
Mike. Please take this mic.
condition number is defined as products of norm of A and norm of A dagger, which leads to sigma max by sigma min. And then I understand that very small singular value is problem. It leads really to big condition number.
Exactly.
But we spoke about van der Monba matrix, or which matrix was with very close singular values, but no small. There was not small eigenvalues. And can we?
Why there is theory is saying that there is well connected between the eigenvalues and the singular values. Singular values, eigenvalues of A transpose, not A. Understood my point?
Yes, small singular,
Eigenvalues of this.
singular values are problem.
Yes,
But
of course.
very close singular values are also problem. And we showed here that algorithm can be infinitely
Yes.
complexity if singular values are very close.
Yes.
But such matrix is not ill conditioned.
Yes, lambda k minus 1, lambda k, this is whole to the power k. If they are very close to each other, this is going to 1. No convergence.
No convergence.
Because
but this difficulty is not because ill conditions.
yes, what is this Hilbert matrix? They are very dense. They are very close to each other.
Yes, and it is
And
problem
if we,
for algorithm.
yes,
But,
yes, that you have to make the stable algorithm.
It is different kind of difficulty than small singular value.
What different?
Kind of difficulty. What is with condition number? Condition number then can be normal, how to say, not so big. But we will have problems
yes,
because of another kind of...
I understood. Your problem is that how we can make not big that one. So for that you have to do this the small change, the sensitivity of the matrix in the epsilon neighborhood. You have to make the analyze in this with the problem. If you do small change in the epsilon neighborhood, then you can analyze the singular values with the matrices. Understood my point? Perturbation. If you want to analyze the sensitivity of that problem, because they are very ill conditioned, you make the small change in the epsilon neighborhood and you find the spectrum union of lambda of A plus delta A, one delta A norm less than epsilon, and you find the eigenvalues and check that how the behavior if you do small change, this kind of ill conditioning problems.
Okay, if we define ill condition, ill conditioning, that ill conditioning means very big condition number, then matrix with very close singular values but not small is not ill conditioned.
Small in the relative sense. Relative sense. Small means how much? Small in the relative sense. You are changing a small delta A. What is the relative change? In that aspect, you have to think. If it is a small change, then its a corresponding eigenvalue is getting a small change relatively, then it is well. But we avoid a small change, large change, okay, and that context dependent. Got my point? Relative change, the error, in that sense, small, tiny, order of unit round of error. If that much is there, it's okay, fine, we can.
Thank you.
Is there any other questions? Okay, no question, then we'll stop this. Huh? Okay, thank you so much.